Hello, everyone. Thank you for joining us today for our Tech Talk. Today, we'll be discussing diagnosing and providing solutions for various seal failure modes. My name is Nathaniel Reese, and I have with me Will Pomeroy. We are both applications engineers with Parker ORing and Engineered Seals Division. I have a background in chemical engineering and experience in our R&D as well as manufacturing environments as well.
And I am Will Pomeroy. I also am on the applications engineering team. We are also joined by Dorothy. She's monitoring our chat. She'll be working with the Q&A or questions that you all might have during the presentation. And also when we open it up for questions afterwards, she'll also be monitoring the chat then. I will note that all participants will be muted during the presentation, and questions, like I said, can be typed into the Q&A section during the presentation, and we'll unmute at the end when we have our time for questions.
So we'll go ahead and get started with the content of our Tech Talk today. Again, we'll be going over the various failure modes that can be experienced. There are a wide variety of failure modes that can occur, but today we're going to be going over some of the more common ones that might be more frequently encountered. And again, as we go through each one, we will also discuss the design practices that can be implemented to prevent these from occurring from the onset.
All right, so to kick us off, we tried to break up some of these failure modes into different genres. So first one we're trying to talk about today is improper gland design and the failure modes that are a result of that. And three that we really kind of landed on were installation damage, extrusion and nibbling, and overfill. In the next few minutes, we're going to go over these in much more detail and also recommend best practices as far as how to avoid them in applications and also how to diagnose it. That is the root cause of a failure. The first one here, installation damage. Our apps team is routinely asked to review parts that either are damaged or they have failed in application, and we're trying to come up with a root cause as to why that failure is happening. And installation damage is a common failure mode that we do see. Results in parts that are sheared, torn, nicked, or cut. And you can see from these pictures here, you would have a pretty absolute, or the pictures show the damage, physical damage to the parts. So the first one in the top left there, it's a slice, and that would be consistent maybe with a part that's rubbing up against a thread or a sharp corner during installation. The second one would be a nick, so perhaps a burr that's in a bore, or also during installation that's getting pushed in there, or perhaps an installation tool that's pinching it while it's being installed. These are all things that can happen during installation from sharp corners, burrs, threads, and the like. This short animation here kind of shows what happens to an O-ring when you have a sharp corner that is being pushed against it during installation. Quite literally pinches the O-ring and would far exceed the elastomer's ability to handle that type of contact force, and it would result in the part either shearing or ripping or being torn to shreds. So a way to combat that, you would add in a lead-in chamfer that would help alleviate that sharp corner, and from that point it would make much easier installation. Ways that you can combat this installation damage would be, one, make sure your procedure for putting the parts in is a best practice. So avoiding installing over threads. That would mean protecting the seal from threads during installation, whether that would be putting a cover or a sleeve over top of them. For parts that do have sharp corners, we would recommend removing that sharp corner and putting a chamfer on there, an appropriate chamfer for either male, radial type sealing. And lastly would be what we would call groove housekeeping. That would be ensuring that your groove is free of burrs or sharp corners, to make the assembly process as safe as possible for that elastomer.
Now, another failure mode that could theoretically be confused with for installation damage, because it also involves separation of material from the seal, would be extrusion and nibbling. And this is a failure mode that basically comes from material being separated from the rest of the seal as it's forced through a clearance gap between the mating components. This failure mode is going to be characterized by the appearance of the material being very chewed, shredded. It's going to be a much more visually incongruent, I guess you could say, form of separation of the material from the rest of the seal. And there's going to be oftentimes, if the extrusion is bad enough or the application conditions provoke it, a much more significant amount of material that's removed and permanently deformed. This animation here displays what happens when extrusion occurs. As the system is pressurized and the seal is exposed to the high pressure under next to too large of a extrusion gap, the material is forced through that gap, permanently deforming and resulting in the seal no longer applying sufficient sealing function. One way to remedy this, or to prevent it from occurring, is when you are designing your gland, you can reference this chart that's in our ORing handbook, and it plots for materials of various hardnesses the behavior that can be expected as far as the pressure that can be withstood as a function of the clearance gaps in the hardware. Now you can see from this there are limitations even for the hardest and most extrusion resistant compounds. So if going to a harder compound still isn't enough reinforcement, you could also consider introducing a backup ring. A backup ring can consist of elastomeric compounds as well, but if an even more extreme solution is required, you can go to a PEEK or a PTFE backup. You can also go to an S-seal or a T-seal if an O-ring with a backup ring combination is not considered sufficient enough. This animation depicts what this solution looks like, or both of these solutions are going to be depicted in two different animations. But this first one shows the impact of having a reduced extrusion gap. You can see as that gap is reduced from being too large as it was originally, the system is pressurized and the material doesn't have as much room to escape and be separated. However, if the clearance gap cannot be reduced, this animation shows what the introduction of a backup ring would provide. As the system is pressurized, that backup ring is basically blocking off the seal from the clearance gap and preventing it from being able to extrude. The backup ring essentially blocks or even takes the hit for the O-ring, make sure that it's not separated from the rest of the seal.
So for this next topic here is overfill. And I'll say that overfill has the potential to look very, very similar to extrusion in that a notable difference would be that you would see it on both sides of the seal. And what overfill is when you have too much seal material, seal cross-section for the groove space that's designed into it. So the O-ring takes a set and has a visible ridge over the edge of the groove is one way you'd be able to see that. And these pictures are also indicative of what we would expect for overfill. This next slide here is a good animation of what this looks like in practice. So as the seal is compressed, you can see there's nowhere for the O-ring to go. The groove space is too small for the seal to be able to deform into it. So this is indeed a gland design issue because the gland is either too shallow or too narrow for the seal to be able to deform into without being pushed up into that gap between the hardware. Some more things that you'll see along with this is that the installation force would be quite high because you are, as void space goes down on groove, the compressive load requirements would go up significantly. So again, overfill is the insufficient void space in the groove, meaning that the seal area is larger than the available space in the groove. And I will also note that excessive swell can be something that causes overfill. So overfill, I guess, can be considered design, and it also can be a result of material selection, but excessive swell on system fluids, so make sure you have that in consideration. And then also the temperature of the application. As elastomers get heated up, they will swell from thermal expansion. So you need to make sure you have that, especially in high temperature applications, that you have considered that impact for your allowable groove space. Some best practices: make sure your gland design is appropriate. We have many resources available for figuring out gland fill percentage and the recommended ranges that we have for different application types. Another would be material choice, making sure that you have an elastomer that is compatible with the fluids that you're working with, as to avoid excessive swell of the seal material. And lastly, making sure you are have a good grasp on what temperature range that your seal is going to see. As you have high temperature applications, you can have overfill as a result of thermal expansion. I'll also note, you see that picture up in the top right, we have technology as far as hollow extrusions to help combat overfill. If that is a main failure mode that you are running into, we can do that through our extruded and spliced material line.
Now, another realm of failure modes are those that have more to do with the material selection of a seal rather than the mechanical aspects of the gland design. So we'll go over some of those failure modes now, those being rapid gas decompression, commonly known by its acronym RGD. We'll also talk about chemical attack, and then ozone attack as well. RGD, or rapid gas decompression, is a failure mode that's characterized by cracking, splitting of a seal, as well as blistering that typically is more visible as soon as the seal is removed from the application conditions. Now, RGD is basically a failure mode that occurs when a system is highly pressurized, and when it's highly pressurized, it allows a gas that's being sealed to permeate into the seal material. Then when that system is rapidly decompressed, the gas that's permeated into the seal wants to escape the seal at a proportional rate. However, the physical properties of that seal material prevent it from doing so. And so the gas basically just rips straight through, causing these tears and these fissures. Something to consider when you think that RGD may be occurring. So one, think about the media that you're sealing. This really just occurs in systems that involve a gas as the fluid that's being sealed. Isn't really seen with liquid. You also want to consider the application pressure. The pressure needs to be high enough so that when it decompresses, there's a significant reduction in the energizing of the system. You also especially want to take into consideration the decompression rate. We consider any application or environment where there is decompression of 200 psi per minute or more to be one where RGD failure and damage is highly likely. You also want to consider the number of decompression cycles that occur, because of course the more that this decompression behavior occurs, the more likely for the failure.
All right, so this next one is chemical attack. And chemical attack, just like it sounds, is when the chemical that you are sealing is going to be attacking the seal material. So what that really looks like is that in application, you'll upon removal of the parts or failed parts, you'll see softening, perhaps excessive volume swell. Again, blisters can be a characteristic of chemical attack. It can be cracking or drying out. All of these things can be chemical attack. And I will say chemical attack can look like a lot of different failure modes, I believe, but it would be indicative of this fluid that's being sealed and the interaction between that and the seal material. So for chemical attack, what will parts look like? Well, when they're removed, if they are soft and gummy or have excessive swell, and what I mean by excessive swell is you have the original cross-section size, and once it's been exposed to a media or fluid that it's not compatible with, the seal will either grow substantially or it could also shrink. Sometimes components or portions or chemical structure of a seal can leach out and cause the material to shrink. Other times, swell would be the inverse, right? The seal is absorbing some of that fluid. And go back to chemistry, is that like with like, that same is like dissolves like. So if you have a situation where you have a seal material that's a good way of determining compatibility. So ways to combat or eliminate risk for chemical attack happening in your application is make sure you have a good material choice. Material choice is going to be something that's always asked. When we have a new application that comes into us, we're generally going to ask 3 questions: and what material or what fluid's being sealed, what pressure load, and then what temperature range is the seal going to be exposed to. And those 3 things in combination help us arrive at a suitable material. Material choice, you would have an example. So if I were to be asked about a water seal, my first go-to would be an EPDM, because I know that EPDM is very, very compatible with water. I would not recommend an EPDM for an oil type application. So knowing what fluids your application is actually going to be sealing is a very important component when you're making these decisions. And also temperature. As temperature goes up, reactivity also goes up. So say that you have an H2S question. We get that pretty often. H2S is not as scary as it normally would be at low temperatures, but when you increase that temperature, it's exponentially more difficult to come up with a seal material that can handle that. So it's important to consider application temperature as well as the fluid when you're coming up with a suitable seal material. And we are happy to help with that if you run into questions.
Another form of attack that's frequently encountered is that comes about as a result of exposure to ozone. As far as compounds or materials that are frequently used for seals, this is primarily experienced with NBR, which is short for nitrile or acrylonitrile butadiene, also known as Buna-N on occasion. This basically occurs when NBR is used in applications such as environmental ones, where even atmospheric levels of ozone can attack the polymer structure of this compound type. This is even more likely to occur when the seal is stored in a stretched condition. So that should definitely be avoided. But whenever it comes to environmental sealing applications, we prefer to go with something like an EPDM or a silicone or an HNBR. If something more, higher temperature or more wear resistant is necessary. HNBR is hydrogenated nitrile, and it has basically undergone a synthesis process that removes the weak point in the polymer structure, allowing for that ozone attack. So you really want to pay attention to your material choice, as Will was just discussing. When you're talking about applications where even atmospheric amounts of ozone could be encountered, you also want to pay attention to your storage conditions. Make sure that you're not sealing NBR rings in a stretched condition in air, and storage conditions at higher temperatures could leave them more prone to ozone attack as well.
So these next couple topics here are what we consider to be a hybrid of either material selection for a failure mode or as a result of improper gland design. So compression set, I would say, is likely the most common failure mode that you'll see within an elastomer. And what I mean by compression set is an O-ring's permanent deformation from its original cross-section shape or size. So what that is, you have an original round shape, 103, 139 cross-section part, and after it's been in a groove and in application, you remove it and it has a squared off look or doesn't quite recover to its original shape. We would diagnose that as compression set. So important things to note about compression set is that generally it's going to take the shape of the groove, but also it's important to note that it'll generally take or show flatness on both sides of wherever that contact pressure is. So for a face seal, you would have that on the top and the bottom of the seal. Whereas for a radial seal, you would have flattening along the ID and OD. And again, it's important to note that it's going to be present on both sides in most applications that we see this failure mode. This animation here is kind of depicting what compression set looks like, as you have a male radial seal here, piston inside of a bore, sealing a fluid. And that seal, whatever amount of time, X amount of time. And after a while, it begins to leak. And when you take that seal back out, you'll notice that the seal, it isn't round anymore. It's taken the shape of that groove and it's not recovered to its original round cross section. And we would diagnose this as symptomatic of compression set. I will also note that compression set can simply be end of life of a seal. It doesn't necessarily have to be a smoking gun for an early failure. It could just be end of life for a seal. So best practice is to try to minimize risk for compression set, again, is material choice. I can't stress how important material choice is. You can have everything else designed correctly, but if you don't have the right material in there, the system will fail. So knowing how material performs at certain temperatures as far as compression set, and also whatever the fluid is. So parts can take compression set faster, or certainly the theme would be that parts take compression set faster at higher temperatures, but it can also be exacerbated by exposure to fluids. We have a common test report method that we'll have. Almost all elastomers, I would say, on our testing, we go through compression set. So generally 22-hour, 70-hour testing, and you'll see a percentage of set that's taken by an elastomer. And you can use that information to try to come to a good conclusion or a good selection for your seal material to combat or minimize risk of compression set.
Another failure mode that can often be confused with compression set is abrasion and wear. And it's easily confused with compression set because it also deals with a flattening of the seal from its original, at least relative to its original shape. But abrasion and wear occurs in dynamic applications where the seal is moving in relation to the gland hardware in some way, shape, or form, whether that's reciprocation, oscillation, or rotary motion. Basically what happens is just over time, the seal material is worn away in very small amounts. And this is identifiable by the fact that there's a flat region, an uncharacteristic flat region on just one side of the O-ring or a seal, as opposed to both sides, as typically occurs with compression set. To prevent this from occurring in your gland or in your sealing application, you definitely want to consider your gland design. For dynamic applications, we recommend, for instance, a reduced amount of squeeze or compression compared to what we would for static applications. You also want to take into consideration your surface finish. We consider most ideal surface finish for your sealing surfaces in your hardware to be about 10 to 20 micro inches RMS. Anything less than that is a little too fine. The micropores left in the sealing surfaces with that ideal surface finish basically allow for retention of some of the fluid that's being sealed to act as a bit of a lubricant. You also definitely want to take into consideration the nature of the dynamics of the application, and make sure that it doesn't involve motion that's too slow, but also, of course, too fast. And you want to consider your material and make sure you have a sealing compound or material that is sufficient for dynamic applications. We never recommend, for instance, a silicone compound or a fluorosilicone compound for dynamic applications. We would prefer to go with something like an HNBR that's more wear resistant on average, or something like an internally lubed compound as well.
Well, we hope that this has been very helpful for you, but I will also say that we have tools available out there beyond this application engineering team and this webinar for diagnosing failure modes. So we have our ORing handbook, heavily used in the industry, and in the back of that, there's an appendix that discusses failure modes and is largely an overview of what we've talked about today. It will give pictures of failures to help you diagnose, but also recommend best practices as to how to avoid them in design. And also for our Inform tool, there is a troubleshooting portion of that tool that's available online as well. You can find that by going to parkeroring.com. And a little bit down the page, there's a tile for our Inform. Other ways that you can reach us, we have our email box for our applications engineering team. It is oesmailbox@parker.com. There's a team of us that monitor that mailbox and do our best to get replies out very quickly to you. We're also available by phone. Our applications engineering, the hotline is 859-335-5101. And our team is able to help with material recommendations, gland design. We can do FEA, failure analysis, and also help you find a good resource for procuring our parts. And at this time, I believe we can open this up for questions. Thank you all for your time.
Everyone is currently unmuted, so if you want to ask questions now, you can. There was a question in the chat asking if we will share our slides. What we will do is we will send a link out to everyone shortly after the recording.
Okay, there was a question early on about having access to the software that we have available to help calculate the groove size. And this was mentioned in the overfill section. We have two resources on our website. If you are to go to the landing page of www.parkerorings.com and scroll about halfway down, the first resource is called Mobile Inform, and that one has been around for about 10 years. And that is an online calculator that will output the results of expected gland fill. The second resource is right next to that one on parkerorings.com. And that one is called the Sizing and Selector tool. And that's a sophisticated interface for you to select your O-ring size and see the output of the hardware. All right. There is another question that was posted to the group asking if there is a good way to prevent spiral failure. Spiral failure, there is a design section in the O-ring handbook. So as a starting point, we recommend leading with the design principles that are listed there. And a few of those off the top of my head include using the recommended O-ring sizes. There are a number of O-ring sizes that are standard and offered, but not recommended for dynamic reciprocating movement. So staying within the suggested O-ring sizes is a good way, and that has to do with the ratio between the ID of the O-ring and the cross-section of the O-ring. Other inputs to spiral failure might be lack of when the piston is side loaded with inside the bore, or if there is an eccentric condition, that might also be an input that results in spiral failure. Outside of an O-ring, there's a number of seal options that would not spiral fail or would be much less likely to. Some of those might be any kind of a seal with a wider stable base, not a round base. For example, like an X-ring or maybe a D-ring, anything that would not have that tendency to roll. Those are some alternative options for preventing spiral failure.
Unless anyone has any further questions, we're going to go ahead and end the meeting now. Again, we appreciate your time. Thank you very much.